Here is a question. Read it carefully and think about the answer. Let us solve it step by step. Let us first understand the key concept here. In electrophilic addition of HBr to alkenes, the rate-determining step is protonation of the alkene to form a carbocation intermediate. The activation energy, delta G, for this step depends on the stability of the carbocation formed, Hammond's postulate, more stable carbocation lower activation energy for its formation. Moving on to the next step. Identify the carbocation formed in each reaction. A. Ethylene, unsubstituted alkene, protonation gives a primary carbocation, CH3CH2 plus or simply primary. This is the least stable carbocation. B. A monosubstituted terminal alkene, like propene, Markovnikov protonation gives a secondary carbocation, more stable than primary. C. A disubstituted or branched terminal alkene Markovnikov protonation gives a tertiary carbocation, even more stable. D. A trisubstituted highly branched terminal alkene where the internal carbon upon protonation gives a tertiary carbocation with more alkyl stabilization, or the alkene is such that protonation gives the most stabilized, tertiary, carbocation among all options. Looking at structure, D, it shows CH2 is equal to C with two alkyl chains, ethyl and propyl or similar, meaning the substituted carbon already bears two carbon groups, so protonation of CH2 is equal to and gives a tertiary carbocation at the more substituted carbon. This tertiary carbocation is the most stable among all four options. Moving on to the next step. The transition state for carbocation formation resembles the carbocation, endothermic, late transition state. The more stable the carbocation, the lower the energy of the transition state, and therefore the lower the delta G. And for the final step. A. Primary carbocation highest delta G. B. Secondary carbocation lower delta G. C. Tertiary carbocation even lower delta G. D. Tertiary carbocation with maximum alkyl substitution hyperconjugation lowest delta G. Option D involves addition to a terminal alkene where the resulting carbocation is tertiary and maximally stabilized by alkyl groups to ethyl-propyl groups, making it the most stable carbocation and thus giving the lowest activation energy. A. Forms primary carbocation, highest barrier. B. Forms secondary carbocation, lower than A, but not the lowest. C. Forms tertiary carbocation, lower than B, but the alkene in D gives an equally or more stabilized tertiary carbocation due to greater branching hyperconjugation. D. The terminal alkene in D has two large alkyl substituents on the internal carbon, so protonation at the terminal CH2 gives the most substituted and most stabilized tertiary carbocation, resulting in the lowest delta G. Therefore, the correct answer is D. Therefore, the correct answer is option D.